Next, we're going to talk about graphing square root functions as part of our Step 17 guided notes. A square root function is simply another type of function, and when we learn about new groups of functions, we always like to start with the parent function so we understand what it looks like as simply as possible. And then we will do many transformations to that square root function or radical function and see how that moves it around our coordinate graph. So if I were to just graph y equals radical x, that's the parent function, or f of x equals radical x. The way we make any graph is just with a t-table, if we're doing it by hand, when x is -1. Actually, I'm going to start even a little lower. I usually like to do -1, -2, 0, 1, and 2, just to get things going. Well, if I put a -2 in for x right here, I can't take the square root of -2, so I would just say undefined. Same thing for a -1. We can't take the square root of -1 and get a real answer, so undefined. That means I can't graph these points. But 0, what's the square root of 0? 0. What's the square root of 1? 1. What's the square root of 2? It's a decimal, 1.57, I believe. I don't like to graph numbers like that. So instead, I'm going to go to the next number that would give me an integer answer, like 4. What's the square root of 4? 2. And you'll notice here, these points are very easy to plot. 0, 0, 1, 1, 1, 2, 3, 4, 2, and so on. I believe the next one would be 5, 6, 7, 8, 9, 3. And you can see where the parent function comes from. When we look at this parent function, the domain is all positive numbers, because when we think about domain, we're just looking at the x values. So as I move across this yellow line, when do I get to the graph? It starts right here. And from here to the right, I have the graph, not over here. This is where x is positive. We are going to use interval notation. So we would write 0, infinity. It's okay if you don't put the positive next to infinity. You could just write it like this. We used a closed bracket because it does include 0. See on our table, x can equal 0. And then we use an open bracket because it never really stops with infinity. When we look at the domain, now we're looking at the y values up and down. So again, as I start at the bottom and go up, I don't get to my graph until here. And from here up, that's where the graph is, as I go up. There is no graph down here when y is negative. So again, same thing, 0 to infinity. Intercepts, where does it cross the x-axis? Right here at 0. Where does it cross the y-axis? Right here at 0. There is no symmetry with this function, unlike the square root function. There was a line of symmetry straight down the center of it. That doesn't happen with a radical function. And behavior as x, here's our x values. As we get closer and closer to 0, this graph approaches 0. As we go to the right towards infinity, this graph keeps going higher and higher and higher to infinity. So this is the left end, this is the right end. All right, let's try to focus on domain and range. Now, to find the domain, we're trying to find possible x values. So we're simply going to look at what's under the radical and think about what that means. If something is under a square root, it must be positive. this yellow bit must be positive. It must be bigger than or equal to 0. It can't be negative. And then we solve. So now I know that my domain, x must be greater than or equal to -4. And in interval notation, I would write that as -4 to infinity. That's how I'm going to find my domain. Similarly, to find my range algebraically, I'm going to take this x value and put it in. F of -4 equals -4 plus 4. See, I took out the x and put in -4, and then I'm going to simplify that. 0. So my range, that's my lower limit of my range, is 0 to infinity. Now let's take a look at this graphically. Let's go over to Desmos and type this in. Y equals the square root. To get the square root, I'm going to click this button down here. It says show keypad, and I think it's off my screen a little bit. Let's move that down. There it is. Square root of x plus 4. If you look at the graph here, you can see that compared to the parent function, in fact, let me put the parent function in blue here, y equals the square root of x. The blue one is my parent function. I've basically taken this blue function and just drug it to the left 1, 2, 3, 4 places. So if the parent function x was greater than 0, now you can see we can go all the way over here on our graph 4 to the left. So that's another way to think about it, but you can also see that on either the parent function or this example, radical x plus 4, the y values are always positive. All right, let's find the domain and range for the next one. Again, if you do this graphically, you could probably just look at the graph and see that it's going to end up shifting 3 units to the right. So we suspect that our our domain would be from 3 to infinity. But let's do it algebraically. X minus 3 must be 0 or positive. When I add 3 to both sides, x is greater than or equal to 3. That gives me my lower limit on that interval. When I put that back in to find the range, we end up with f of 3 is the square root of 3 take away 3, which is 0. So my range is going to be from 0 to infinity. Probably noticing a pattern here. This problem is different because not only are we adding 6 inside the radical, we're also adding 2 outside the radical. We can't just put these two together, obviously, because this constant is under the radical and this constant is outside the radical. So let's set just the part under the radical. Let's say that has to be positive as we find the domain. X plus 6 must be greater than or equal to 0. When I subtract 6, x must be greater than or equal to -6. So my domain is -6 to infinity. Now I'm going to look at the range. F of -6 is the square root of -6 plus 6 plus 2. This gives me 0 plus 2, which gives me 2. So my range is from 2 to infinity. And if we look at that on a graph, I'm going to leave my parent function. Y equals the square root of x plus 6 plus 2. This green graph has been shifted 6 to the left and up 2. So instead of my y values being greater than 0, now my graph doesn't even start until I get to 2 on the y-axis. From here up, there's green graph. But if I'm down here, there's no green graph down in this range. Down in this area, there's no green graph. Let's talk about these transformations and see if we can figure out some patterns just looking at them. A lot of what's written in this key concept chart is a little abstract because we're dealing with just variables and no numbers. It makes a little bit more sense, in my opinion, to look at it with numbers first and then go back and see how these rules can apply. Let's just use the graphing calculator to graph this function. I'm going to use the Desmos calculator first. X minus 2, and then add 5. All right, again, if I need, I can turn off my parent function if it's in the way, just by clicking on it. But you can see that this green graph is the same as the blue graph, but it's been shifted to the right 2 and up 5. This number under the radical controls the horizontal translation. It controls whether it goes left or right. The number outside the radical controls if it goes vertical, up or down. And vertical is very intuitive. If you add a number, it's going to go up. If you subtract a number, it's going to go down. So I'm going to put that off to the side here. Add a number outside, the graph will go up. Subtract a number, outside, the graph is going to go down. And you can see here in the abstract, if k is positive, it goes up. If k is negative, it goes down. Makes much sense. Under the radical, it's like basically the opposite. If we have x take away 2, it's going to go to the right 2. If this was x plus 2, that would make it go left 2. So what happens under the radical is kind of the opposite of what you think. And the reason that is because of the main parent function formula here. So I like to say that when we have x plus a number, we go left. When you see x take away a number, we're going to go right. That many units. So this one, if we look at our Desmos calculator, we can look at a table of values. Let me, oh nope, I didn't want to do that. I just pressed the button right up here at the top that had the gear. When you press that and then press the table, it'll give you a whole list of values. Now notice for negative numbers it's undefined. At 0 it's undefined because if I put a 0 here, this would not, we would have the square root of negative 2. Same with 1. Once I put a 2 in, I get the 0.5. So I'm going to also put 3, 4. I'm just hitting enter, 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 enter. And our goal is to plot points with integer coordinates. 2, 5, 3, 6, 6, 7. These are all nice points to plot on our graph. 2, 5, 3, 6, 6, 7. 2, 5, 3, 6, 6, 7. Let's see if we can find any more points. I'm going to just keep hitting enter. The next one is 11, 8. let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I fell off the graph, but I'll make it work. 11, 8 would be up here. And then we just connect our points and put an arrow on the end. Let's think about the domain. Since we have a graph, we don't need to think of it algebraically. We can just look at our graph. Look at the x-axis first. As I go from left to right, I don't have blue graph above me until I get to this point. So from here to the right is my domain. This number right here, that number is 2. So my domain is from 2 to infinity. My range, now I'm looking at the y-axis. I start at the bottom and I go up. I don't have any blue graph next to me until I get to this point. And from here up, there's blue graph on the side. This point right here is 1, 2, 3, 4, 5. So my range is from 5 to infinity. The next one, we have a little bit more happening than simply a vertical and horizontal translation. On the next one, we are adding a number inside the radical. We are subtracting a number outside the radical, but we also have some other stuff happening here. So let's address each part individually. We know that subtracting a number outside, that's going to cause a vertical translation or a vertical shift down 1. We know that adding 3 inside, as we've just discussed, means there's a horizontal shift. Remember, we do the opposite, left 3. But what does this negative sign out front? What happens there? Let's go back to our key concept here. And it says that if A is that number out front, if this number out front before the radical is negative, it's reflected across the x-axis. So this graph is getting flipped over the x-axis. Instead of being a function like we've graphed where they start here and go up to the right, it's going to start and go down because it's flipped over. That's what we're expecting because of the negative sign. So this negative indicates a reflection over the x-axis. How about this number 2? What does that do? Well, if you check your key concept, if that number is bigger than 1, 2 is bigger than 1, it's stretched vertically. That means instead of just being a function like this, it's going to be stretched up a little bit, stretched vertically by a scale factor of 2. So this causes our vertical stretch. So let's type this into Desmos and see what it looks like. I'm going to get rid of that function. I'm going to type y equals -2 times the square root x, and I forget what my function is already, x plus 3 minus 1. X plus 3, right arrow, oops, I need to stay under there. X plus 3, right arrow to get out of the radical, minus 1. Notice looking at our blue parent function compared to our red new function, it has been reflected, so it's flipped over. It's shifted left 3, down 1, and it's a little bit stretched. So if we look at a table of values, we will have some nice numbers that we can plot. -2, -3. Oh, and I just realized the graph may have cut off, so I'm going to the next page. -2, -3 to graph this actually. Let's see, the next nice integer coordinate point, 1, -5. All right, and I'm out of points, but I'll continue on. 3, 4, 5, 6, -7. That's a nice integer point. Over to 6, down to 7. All right, can we get any more nice points by hitting enter? 13, -9, that's going to fall off my graph, so I'm just going to start with these. Actually, I'm also going to go up in my graph. -2 was this point. Let's see if I can't capture that point. Let's see if I type -3. Oh yes, -3, -1 is a nice point, which we expected to have on our graph. So now I will just connect these. And let's talk about our domain and range, just looking at the graph. Okay, again, as I move from left to right, I don't have graph underneath me until here. And from here to the right, I have graph underneath me. So that is from -3 to infinity. My range, my y values. Now I'm thinking about my y values. I'm going to start at the top this time because it's been reflected. I don't have any graph next to me until I get down here. From here down, I have graph. I have the function graphed. So that is from -1 down to -infinity. So think about a number line. -infinity would happen first, all the way to -1. So do you see when it's been reflected over the x-axis, our range is actually going to have the -infinity on the left and the number on the right. So be careful with that. That does make a difference. Next video, we will learn the details about graphing cube root functions.